morning. This is Grand Rapids Community College's calculus class. Last class period we had an exam covering some of the applications of integration. And today we're going to begin talking about some of the next sections. I'm starting, it's a new little schedule here that I printed out. I have sent an email to Luann out there at Byron Center. She should be able to print off these for you guys. If she isn't able to, I'll try to bring some out on my way back home today. Essentially, should have made it not quite so fat. So essentially today, Friday the 13th, again, the second Friday the 13th of the year. I guess there's another one coming later too. But anyway, not superstitious. So today we're going to try and cover 9193. Chapter 9 involves differential equations. Many of you might take a differential equations class later. We're just intending to introduce you to them. Section 1 is just an introduction to what is a differential equation and verifying solutions of differential equations. Section 3 is one particular type that we call separable. Because if it's separable, if the differential equation is separable, we can actually solve it using techniques we already sort of know. 9.4 is applications of differential equations to population growth. So we're just going to do one set of applications there. So today and Monday we'll talk a little bit about differential equations. Then on Wednesday we'll do a little bit of chapter 10, which is another sort of a mishmash of a couple of topics. Parametric equations and polar coordinates. So the first day there we're going to introduce them. If you haven't seen them already, sometimes some of that you may have seen or may not have seen before. And then 10.2 is where you apply parametric equations to calculus. 10.4 is where we're going to apply polar coordinates to calculus. And then we'll review and a test in 2 weeks. So then after that, April will mostly be totally consumed with chapter 11, which is a pretty long chapter on series and sequences. So, so that's our general schedule. So we're going to start out talking about differential equations today. So a differential equation is an equation that involves a function and its derivatives in some way. Other way around. You might see them, sometimes we write them like this. So here I have x as a function of t, so I have the second order derivative of x with respect to t, plus some constant times the first order derivative of x with respect to t, and equals some other function of t, which isn't x over here. This is just one example. There's lots of examples. Sometimes we'll write them like this. Y prime plus ky equals c. If we use the prime notation, the implication is typically that the variable is t, but it could be x. A lot of it depends on how we're applying it. So rarely in differential equations will you see it written in this kind of form. For whatever reason, we often use the function notation for something on the right-hand side of our differential equation, but we rarely use the standard function notation on the left side. So either we use just this, the prime notation without the parentheses around the x, or we use the derivative notation like this, but very rarely will you see it written f prime of x like that. It just isn't usual. I mean, these would be the same equation, but we don't usually write it this way. We usually write it that way. So where do we get differential equations from, and why maybe we want to study them? Well, differential equations, just like derivatives, represent rates of change. So it turns out that it's very natural in a lot of our studies to talk about how things change might be related to the function itself, for instance. So here's an example. So one of Newton's laws talks about force being equal to mass times acceleration. And if we were talking about a spring, we've learned that the force on a spring is proportional to its displacement and in the opposite direction. So if you pull on a spring, the force being applied to it is going to try to pull it back the other way. Or if you push down on a spring, the force is going to try to push it back up. So whichever way you push the spring, it's going to want to go the other way. So if you let go, it pops back. Well, acceleration is the second order derivative of displacement. Velocity is the first derivative, acceleration is the second derivative. So I'm going to set these two equal to each other. Mass times acceleration equals the force due to the spring displacement, and then I'm going to replace acceleration with the second derivative, and we have a differential equation. Now, we're only going to deal with a few of these that we're going to solve. Some of these in the first section, you're just going to have to verify that something's a solution. But let me ask you to see if we can come up with one just by looking at this. This is telling me that the second order derivative is proportional to the function itself, but opposite in sign. So can you think of a function, when you take the derivative twice, you end up with the same function back, but opposite in sign? Yep, sine, cosine, either one of those would represent one possibility. So let's assume x equals some standard sine function. So I'll just call it a sine of wt. Now we want to find a and w so that this solves our differential equation. So I already have x. I'm going to be able to take this and stick it in for x. But I have to figure out the second derivative. So let's go through that. So dx dt is going to be a cosine of wt, or omega t, times omega. And then the second derivative is going to be negative a times the sine of omega t times omega again. So we end up with this squared. substitute in on that side. So I have m times negative a sine of omega t times omega squared, or w squared, equals negative k times a times sine of omega t. All I did was put what we just solved for the second derivative in for the second derivative in the equation, and I put what we had written down as x in for x, and then we're going to cancel off what we can. There's an a in both sides, there's a negative sign on both sides, and a sine of omega t on both sides. So I'm left with m omega squared equals k. Omega squared is going to be k over m, and omega will be the square root of that. And I guess we could use plus or minus, but we'll just... The sine function is an odd function, so it does change it a little. So I guess I should... Now you notice that a didn't matter because a is canceled, so a can have any value. So my solution is going to be a sine, or one solution, a sine of the square root of k over m times t. Okay. So let me give you one more where we want you guys to try to show that a certain function is a solution of a differential equation. So essentially I'm going to want you to take the derivative here, plug it in, and plug this in for y, and show that it actually works out. And if necessary, you might have to find a particular value for c, although it might, like my a, it might work for any value. Okay, so I took the derivative. This was a quotient, so I used the quotient rule, which was derivative of the top times the bottom minus the top times derivative of the bottom all over the bottom squared. So that's simplified to 1 minus the natural log of x minus my constant c all over x squared. I then put this into the differential equation for y prime, the natural log of x plus c over x, and for y. And notice the denominators in both cases canceled. So I have 1 minus the natural log of x minus c plus the natural log of x plus c. Those are all just going to cancel. I get 1 equals 1. So it's true no matter what c is. Sometimes, like I did last time, it only was true when my omega was equal to some combination of the constants. In this case, it's always true. Is that okay? Questions, anybody? All right, so sometimes they'll say, now this is maybe a general solution because it has a constant there. They might ask you to find they might ask you now to find a solution that satisfies the initial condition. It's kind of grown to become the word initial there was often used because so often the data value we knew was when t was 0, but we use it anyway, even if the x value is not 0, we use it as the initial condition we need. So we need to know one point. It's kind of like trying to find the slope of the line. You need to have a couple points to figure out the slope. So all I'm going to do now is go back up to my y. And figure out what c is that makes this true. So y equals 2, another way to read this is y equals 2 when x equals 1. So I'm going to put a 2 in for y and a 1 in for x. So 2 equals the natural log of 1 plus c all over 1. But the natural log of 1 is 0. So c equals 2. And my equation becomes y equals the natural log of x plus 2 all over x. So, like the word we use for this is initial condition, the words we use to describe this solution, where we found a value of c, is called a particular solution. This first one's called the general solution, and the second one's called a particular solution. Like I said, it's very similar to finding the y-intercept, say, for instance, of a family of lines that all we know their slope. Okay. Another thing in this first section where we're introducing differential equations is a little bit of analysis of the equation itself. This one's quite a bit more complicated than the one we had before. But I want to factor the right-hand side here. So I can take a y squared out of everything. And I can also factor it into y minus 1 times y minus 5. So sometimes we have solutions to differential equations we'll call constant solutions, or another broader set are equilibrium solutions. Equilibrium solutions are ones that once our system, once our function reaches that state, it will always solve. It won't have to change from that point. It becomes equilibrium. So it's the value of y. In this case, these are going to be constants because there's no function over here. So in this particular differential equation, the equilibrium solutions are constant solutions. Values of y that make my rate of change of y 0. So if I were graphing my function, these would be my critical points. But here they're equilibrium points in terms of if y was, say, 1, for instance, once it reaches 1, it's not going to change anymore. Because y minus 1 here, this term goes to 0, and dy dt would be 0, and so it's not changing anymore. So that becomes a constant once it reaches 1, or 0, or 5. Those would all be constant solutions or equilibrium solutions. Okay. And then you can ask yourself, so these would be at y equals 0, 1, and 5. You can ask yourself this question. What is y if I were to plot these on a number line, like we did before for looking at increasing, decreasing? We can ask the same sort of questions. Is y increasing or decreasing in between these values? There's a slight difference between this and what we were doing in Calc 1. What variable am I talking about here? These are y values, not t values or x values. When we were finding critical points before, we would take the derivative. We'd have y as a function of x. We'd take the derivative, solve it for x, and then we'd have a number line like this in terms of x or t. But in this case, this is my function that's over here, not the time. It's over here. Okay, a little bit different. Okay. But anyway, you might be asked, where is this graph? And this is y. Where is the graph? The function increasing. For what values of y? Let's see if I can write this the right way here. For what values of y? Is y increasing, for instance? You might be asked a question like that. Now in this case, I can go back through and look at this. If I pick a y value that's less than 0, y squared is going to come out positive, y minus 1 is going to be negative, y minus 5 is going to be negative. So I'd have a positive times a negative, which comes out positive. So y is going to be increasing there. When I look at values between 0 and 1, again, y squared is going to be positive. Same thing, actually. Once I go past 1, it's just because the y was squared. Nothing changed there. Once I go past 1, so I'm between 1 and 5, the first factor is still positive. Y minus 1 becomes positive. Y minus 5 is negative. So over that interval, y is decreasing. And then to the right of 5, for y values greater than 5, it's always increasing. Now, if we were to analyze our constant solutions here, 1 is the most stable. If somehow I were to drift away from 1 in either direction, suppose I went down, so y drifted away to a little less than 1, what's going to happen? According to my differential equation, it's going to increase back up to 1. And if y were to drift a little bit to the right of 1, according to this, it's going to decrease back to 1. So this is a very stable solution here, constant solution that in real life, settings don't always stay where they're at, and that's why we're talking about this. Mathematically speaking, once y reached 1, it should never change, but in real life things do change. But this is saying if it drifts a little bit one way or the other, it's self-correcting. It's going to bring it back. Yeah, Michael?
I think you answered my question. But what do you mean by stable exactly?
Well, that's what it's going to come back. On its own, it's going to come back. This would be, say, 5 here is both 5 and 0 are a little more unstable, but 5 in particular. If I go a little bit to the left of 5, I'm over here 5, what happens? Y becomes decreasing, and instead of staying at 5 or coming back to 5 where it was, it's going to go down to 1. On the other hand, if I drift a little bit to the right of 5, my y value is increasing, so all of a sudden it shoots off to infinity. You get the idea? So this is a very unstable constant solution. Even a slight drift one way or the other end, it's not going to come back. So this is the astronaut out on the walking on the ship, and all of a sudden if he loses track, gone. 0 is sort of in between. If I go left of 0, it comes back. But if I go to the right of 0, it goes up to 1. So on one side, it's not stable, but on the other side, it does come back. So again, it's an interesting little study that you can make without actually even knowing the general solution to the differential equation. You can look at it these almost more generally. And sometimes we do look at them in that sense. We don't try to find an exact solution always. Okay. So I think I went through being able to plug them in. I need to go back and just talk. I forgot to talk one little bit about this. I meant to mention some more ideas here. So I'm going to go briefly just back to my spring equation. So this was a spring equation, very ideal sort of situation. I'm going to add this. We typically put all our function values, when we talk about differential equations, we bring everything to one side that has to do with our function. And then the other side involves maybe what we might call forcing functions or things that are outside my system. So this would be a spring constant, but it's pretty ideal. If I actually took a real spring and plucked it, would it keep oscillating back and forth forever? No. So it's going to slowly stop bouncing up and down until it comes to rest. They call that a damping effect. So it turns out that one model for a damping effect has to do with the velocity. Now I'm going to put B here, but often it's actually negative. The B value there is often negative. This would be a damping term. And then instead of 0 on the right-hand side, we might have some force being applied. I'll just call it F of t, but it's not the x, but some exterior force. So if you were to picture this spring as being more like our shocks on our car, the force here might be the force to the road being applied as you're going up. What force is being pushed on the spring? The rest of this has to do with the spring itself, or the shocks themselves. The mass of the car maybe on the shocks times acceleration, this would be up and down. This is again the damping term, so this represents how well the shocks are slowing that down so we don't bounce forever. And then this K is the spring constant having to do with the shocks. But this would be some external function being applied. Now we've made this quite a bit more complicated. And the solutions to this are going to depend on the values of M, B, and K. And similar to quadratic functions, there's some that are going to come out nice and some that aren't. If our damping is strong enough, then it will settle down. Our function might hit it, but our shocks will settle us down. If you make them too stiff, though, then things can break. But if they're too soft, then it takes a long time after you hit that pothole for the car to stop bouncing up and down. So you get an idea of some of the solutions. We're going to deal with ones, again, in your differential equation class that you may end up taking in a semester or two. They'll get to how to solve these ones. But we're going to deal with more ones we call separable. So let's see if I can give you one. Newton's law of cooling says the rate at which an object's temperature changes when placed in an environment is proportional to the difference between the temperature of the environment and the temperature of the object. Phew. So I need some variables here to try and write a differential equation. So I'm going to let t be the t of capital T of small t be the temperature of my object at time small t. And then what else do we have here? Proportional difference between environment. I need some variable for the temperature of the environment. So we'll say E is the temperature of the environment. And for the sake of just this problem, we're going to say which is constant. So we preheated our oven and let it reach the full temperature before we stuck anything in. Now, this assumption, by the way, Newton's law of cooling, is that the object's not changing state. If it holds pretty true, say if I was talking about water, it holds pretty true when water's water state. Once it reaches freezing, there's a brief time where it changes from liquid to solid when it doesn't quite follow this proportionality. It has to change, the energy has to be used to change the state first. And once it does that, then it goes back to using Newton's law of cooling apply. So how can I write this differential equation? So the rate at which an object's temperature changes, what am I going to use for that? Derivative. So d capital T with respect to lowercase time is proportional, means I'm going to have some constant. We'll use K. And difference means what? Means I'm subtracting. So between the temperature of the environment and the temperature of the object. So I have d capital T, d lowercase t equals K times the quantity E minus T. Now if I look at this, if my temperature of my object is less than the environment, the temperature should increase. So if I put it in something that's warmer, take it out of the refrigerator and set it on the table, it should warm up. On the other hand, if my temperature, capital T here, is bigger than E, then E minus T becomes a negative value, and it means my temperature is going down. So if I take something off the table and put it in the refrigerator, then the temperature should get cooler. Or take it out of the oven and put it on the table. Okay, so how do I solve this? This brings up to solving separable equations. Turns out that when we're doing first order differential equations, we can separate the derivative into its differentials. And we've done this a little bit when we did like substitution, U substitution, or parts, the integration by parts. I'm going to take and multiply the dt to that side, the lowercase dt. So in terms of differentials, it looks like this. But what I'd like to do is I'd like to have all the variables that have to do with capital T on the same side of this equation as my differential in capital T, and any variable that has to do with lowercase t on the other side with lowercase differential dt. So I am going to divide just this e minus t term over to the left. We call that separating variables.
So the left side of my equation now has either constants or a function of the same thing as the differential. The right side has either constants or the same thing as the differential over there. In this case, lots of constants. There's only one variable, and the capital T is on the same side as D capital T is. So now we're going to anti-differentiate. So when I anti-differentiate the left side, I get negative the natural log of e minus t, e minus capital T. On the right side, I get k times lowercase t plus c. I want to solve this for capital T, so I'm going to take the negative sign through everything. Now I left this as plus c because I don't know what c is anyway. So changing the sign on a constant I don't know I don't need to think about that. And now I'm going to take and undo a natural log. I'm going to take e to the power. Now this right side is e to the c times e to the minus kt. It's e to the minus kt plus c, but I can factor out an e to the c part, and then I can create a new variable. Again, I don't know what c is, so e to the c is just as constant as c is, but I probably at this point shouldn't use the same letter, so I'll use a. Let a equal e to the c. It's still constant, but it's just a different constant, different letter I'm using. So e minus t equals a e to the minus kt.
Don't you have to, you switch the negative sign? Wouldn't it have to be negative KT minus C?
Again, yeah, I don't know what this constant is, so you can put a minus sign through this if you want. Um, I still don't know what that constant is, so I've just replaced it with another constant. So if you wanna pull that, um, again, technically going back to original calculus, I should have an integration constant from this integral and another one from that integral, and call them two separate things, and then add them together and call them a third thing. You understand what I do with Eric? We typically just absorb them all into one constant, and until we actually know what the constant represents, we often don't bother with keeping the sign. But if it gets to the point where it represents something different, and at this point, most times they think something in the exponent is different, has a different feeling than some that's multiplied as a coefficient. So here they would take the time to rewrite it as something different. You understand what I'm getting at? It has a different feel to it, so especially in an applied problem. I still haven't gotten to capital T yet, though. some algebra here. So if I subtract e to the other side, negative t equal negative e plus a e to the minus kt. And then I can change all the signs, multiply through by negative 1. So my temperature of my object is going to be equal to the temperature of the environment minus a e to the minus kt. And so I'm going to use T sub 0 to represent my initial temperature of my object. So T sub 0 would equal E minus A e to the minus K times 0 would equal E minus A. So solving that for A would equal E minus T sub 0. So a more specific solution. This is one solution, one way to write the solution, that one there in dark blue. But another way to write it is to solve for the coefficient A in terms of the initial temperature of the object. And if you don't like negative signs, you can write it either one of these ways. So either you can write it as the temperature of the environment minus the temperature of the environment minus the temperature of the object, initial temperature of the object, times E minus KT. Or if you don't, you can change that to plus and reverse the variables. These constants, I should say. You guys have probably seen Newton's law of cooling before in your classes, but if you hadn't, again, if T is 0, then this e to the power becomes 1. You can see how the capital E's cancel, and I just get my initial temperature. As T goes to infinity, the limit is this going to go to 0. That whole term goes away, and my object, temperature of my object approaches the temperature of my environment, which is what should happen. I put a can of pop in the fridge. Eventually, the can of pop should reach the temperature of the fridge, or get close to it. Okay, so that's an example of a separable differential equation. Let me give you a couple here to do. I'll just start out with one that's just so I have dy dx equals 1 over the square root of the quantity, the product of x and y. And I want to find a solution for which y equals 4 when x is 0. So the first step is going to be able to be separating the differential, the derivative here into two differentials. The dx, now remember these differentials have to be in the numerator, by the way. I can't divide the dy down to the other side. That's not the way our integrals work. The differentials will have to be in the numerator. So you need to multiply the dx up and separate the x's and y's. So all the y's on one side, all the x's on the other side, and then See what happens. Then do your antiderivative. So how'd it go? So the square roots we wrote as half powers. I'm going to bring the y, the 1/2, up over on the left side. Bring the dx on the right side. So I end up with y to the 1/2 dy equals x to the negative 1/2 dx. You get there. Then you're going to integrate both sides. And the way you integrate these, then you add 1 to the exponent, divide by the new exponent. So I get y to 3/2, 2/3 y to 3/2, and over here I get 2x to the 1/2, and then you get some integration constant. So I multiplied everything by 3/2, and again, if you want to call this one C1 and this one C2, whatever you like. But I was going to then solve for y, but I figured I'd use my initial conditions here to figure out what C was while things were still in a less crazy state. So when I put 4 in, 4 to 3/2 is 8. Put 0 in for x. I get 0. Yeah.
How come you, why did, okay, got it.
It's okay?
Yep.
I know you could do y to 3/2 over 3/2, but I tend to just do the dividing by fractions, the same as multiplying by the reciprocal, so I tend to just do that. Is that the part you were talking about?
No, something else, but I got it.
Okay. Okay, so I figured out what that constant was. Constant came out to be 8. Substitute that back in. So here I have 3 times x to the 1/2 plus 8. And then I'm going to get y by itself. I have to undo that exponent, so I'm going to take the 2/3 power. What do you think? Again, you guys have calculators. We could check this up here, on our calculator. See if it works out. So I need to zoom in here.
You could have solved just for y before you plugged in the x and the y, correct? And then you would have had
Yeah.
C equals 4, but you just, it would just have been.
Well, no, see, when you take something to the 2/3 power, sum to the 2/3 power, you can't leave that C outside the radical. That's the issue. So it can't stay out there. It doesn't have quite the same effect. Zoom in. Okay, so I'm going to test my solution, see if it works out. So where y is, I'm going to put in 3 times square root of x plus 8, all raised to the 2/3 power. Okay, so on my home screen here, I'm going to ask whether dy dx equals 1 over the square root of x times y. So first I'm going to take and figure out what dy dx is. So on the calculator, I'm going to differentiate y1 of x with respect to x. And then I'll try the right side. It's supposed to equal 1 over square root of x times y. X times y1 of x. So, are these the same? Now, the format came out a little bit different. But when you think about taking the square root of x times 3 times the square root of x plus 8 to the 2/3, the square root of x part is going to come out just like that, 1 squared x. And the square root of 2/3, something to the 2/3 power, is that same thing to the 1/3 power. So these match. So that was good. And the other thing I should make sure is my initial conditions right. So I'm going to go to my table, or I can just ask, what is y1 of 0? And it should come out to be 4, which it was. Yeah, Michael.
So I got confused on that. What the
I'm just checking it, verifying it, right?
Right.
So that first line was the left side of my equation, dy dx.
equation?
The second one should be 1 over the square root of xy,
Oh,
which was the right side of my equation. Now, like I said, my calculator chose to simplify one and not quite simplify the other, at least not the same way. So then you have to make sure they're really the same. But anyway. Okay, let's try one more.
so in the answer to this, you wrote
That one in green.
y. Couldn't you write 4 equals the right side of that?
That's only when x is 0. That's one point on my graph of mine.
Okay.
I didn't try graphing that. Since I have the square root of x, we could graph and see what the solution looks like. Since I have the square root of x, x has got to be positive. So if I look at my window here, I could go 0 to whatever. Let's say something nice like 25 by 5s. And y is going to come out to be positive also. 23. I don't think it's going to be even that big. So 2/3, 23, 2/3, let's say 15 by 5s. We'll see how it looks like. Let me try it on the graph. So there's my general solution to it. And the initial condition is the one that's over here at the left end. When x is 0, y is 4. But it doesn't stay 4. As x changes, it gets bigger. Okay, let me give one more here. Where did I put that thing? That's what happened. You know what? Maybe I'll do. I better not. I better do one of these other things. Since we're doing some other things here. Okay, find the orthogonal trajectories of Okay, what do I mean by orthogonal? Well, orthogonal is a fancy word that we use to really mean perpendicular. Oftentimes it comes out when we start talking about multivariable So how do you describe multivariable if you have 5 different variables as input? So we use the word orthogonal instead of perpendicular. But orthogonal trajectories. So what I want is to find curves that are going to be perpendicular to this curve, no matter what k is, and no matter what x is. So we want to find curves who have a slope that is a negative reciprocal. We want z such that I'll just do z. Such that z dx is negative 1 over dy dx. That's how you find a perpendicular slope, right? Change the sign and take the reciprocal. So first of all, I have to find dy dx. So again, I have this little quotient thing here. Dy dx to the top is just 1 times the bottom minus the top times derivative of the bottom all over the bottom squared. So I get 1 over 1 plus kx squared. Okay, so that means my differential equation for z is negative the reciprocal of that. So when you take 1 over 1 plus kx quantity squared, I just get negative 1 plus kx quantity squared. So I can bring the dx to the other side. This isn't too bad. And then I can do the antiderivative. You do a little u substitution. U becomes 1 plus kx, so du is k dx. You put a k in here and a 1 over k out front. And I get 1 over k times the integral of negative u squared du. So z is going to be negative 1 over k times u cubed over 3 plus some integration constant. And then I substitute back in. I'll put that as 1 over 3k times 1 plus kx to the third. So suppose k, so this is our solution actually. So suppose k was 1. Then my original equation would have been y equals x over 1 plus x. And my z's would all look like negative 1/3, 1 plus x cubed plus some integration constant. So I'm going to just look at this curve, and then I'm going to plug in a few of these and show you what I mean by orthogonal. So y equals 1x over 1 plus x. I could zoom standard, and it'll draw it for me. The problem with standard is the x and y graphs axes are not evenly scaled. So once I zoom standard, I'm going to zoom square, which is 5, and that rescales it. But the problem now is I'm zoomed out so much I can't really see, so I'm going to zoom in a little bit. That might be better. I wonder if I can change it's connecting these. But anyway, so forget the vertical line there. It's just what my calculator is doing for now. I think this is zoom square. Yeah. Okay, good. All right, so now I'm going to go back to y equals, and I'm going to put a couple of these ones in here that I had. And they all look like negative 1/3, 1 plus x cubed. So there's like 1 right here. But I'm going to do the same thing, only I have this plus c, so I can take y3 of x and add 2, say, for instance. And, oops, I didn't do that right. Oh, yeah, I did. Y3 of x and subtract 2, just to have a couple of different ones. So now when I do the graph, what should happen is the functions I get should be orthogonal to my original function. So if you look right at that point where these two cross, they're perpendicular, if I zoomed in close enough. And if I zoom in close enough to any of these values, so let me see, zoom, where is it? Zoom. I guess I've set factors in. But it doesn't look right. I can zoom in and then, but then, I guess I can zoom into whichever one I want. I'll zoom into this one down here. So there's my first equation. And then here's one of the ones that's supposed to be orthogonal. You can see that right at that point, they are perpendicular to each other. So anyway, so if you get a question, I think there's at least one line in the homework where it asks you to do this kind of thing, where you have to find orthogonal trajectories. Take the equation they gave you and find a solution to a differential equation that has exactly negative reciprocal slope. So take the derivative of the equation they give you, take the negative reciprocal of that. That's how we got negative 1 plus kx squared. And then solve that differential equation. Okay. One of the other applications they have has to do with mixing, a little bit of chemical engineering sort of question here. Okay, so I have this large tank of salt water. It has 20 kilograms, right now, initially it has 20 kilograms of salts dissolved in 5,000 liters of water. And then I'm adding salt water to it. So brine that comes in has 0.03 kilograms per liter. Well, this was actually 20 divided by 5,000, so it was 0.004 to begin with, so it was less. This would be more like 150 kilograms per 5,000 liters. So the brine that's coming in has a higher concentration of salt than what I currently have. And it's entering a tank at 25 liters per minute. So, 5,000 liter tank, 25 liters per minute coming in, 25 liters per minute coming out, but the part that's going out is thoroughly mixed. So what's coming in is being stirred, and as it's being stirred, it's some that's going out. And they want to figure out, in 30 minutes, how much salt's going to be in the tank. How is this changing? The salt value should be going up. How much does it change in 30 minutes? Okay, so I want to make a differential equation out of this, and it has to do with salt and time. So of x of t equal the amount of salt in the tank at time t. And this initial value, so x of 0 is going to be 20. So a differential equation should represent how fast the amount of salt is changing with respect to time. And so I'm going to put the rate salt that comes in. Is going to be the rate salts coming into the tank minus the rate salts going out of the tank. The key idea being there's salt. Okay, so we have 25 liters per minute, and that gives me my time unit, and then I'm going to multiply that by, the coming in isn't too bad actually. So the in part is going to be 0.03 kilograms per liter times 25 liters per minute. Because the brine coming in always has the same amount of salt. Notice how the liters are going to cancel here. I'll get something like 7.5, no, actually 0.75 kilograms per minute. Okay, that's the rate at which it's coming in. The rate at which it's going out is a little more complicated. I still have the 25 liters per minute. But the question is, how much, what's the proportion here in terms of how much salt there is? Well, x is the amount of salt I have, so this is going to be x over 5,000. That's sort of my salt density. X kilograms per 5,000 liters. See,
the amount amount of salt that's going out is based on how much salt is in the tank. If it's thoroughly mixed, it's the density of the salt in the tank times the rate at which the liquid is leaving. Does that make sense? All right. So So after simplifying that a little bit, dx dt equals 0.75 minus 1 over 200 times x. Or if you want to solve this, I guess we could write it over, since we have to separate it anyway. It could be 150 minus x over 200. So separation of variables, I'm going to divide the x over to the side that has dx, and I'm going to multiply dt up over to this side. So I get dx over 150 minus x equals 1 over 200 dt. Yeah, Michael. Oh, we lost.
How did you get the 1 over 200 x?
25. I mean, there's letters here that represent units, but it's really 25 over 5,000.
I see what I did. Okay, thank you.
And now we're going to integrate both sides. So I have negative the natural log of 150 minus x equals 1 over 200 times t plus some constant. And now this is very similar algebra to what we used earlier. I'm going to change the sign, take e to the power, change e to the negative c for a. So this becomes 150 minus x equals a e to the minus 1 over 200 t. So x ends up being equal to 150 minus a e to the negative 1 over 200 t. My handwriting's starting to get a little smaller. Now we just have to figure out what a is based on my initial conditions, which x of 0 was 20. So 150 minus a is going to be 20. So a has to be 130. So there's an equation now that represents x, the amount of salt in my tank. They asked specifically for after 30 minutes.
So this is an x times 30, this is x of t. So I'm plugging in 30 minutes. So I get 150 minus 130, e to the minus 1 over 200 times 30. So x is about 38 kilograms. Okay, so I think I'll just stop there for today. 2 sections again, one that introduces differential equations, and one where you're going to do solving differential equations using separation variables. And then Monday we'll do particularly population growth and models for that. Wednesday, we'll skip to the next chapter. So this is more of just a taste. Many of you, like I say, might end up in the course differential equations where you spend the whole semester looking at it. All right. Take care. John, you still don't sound healthy. But I'm probably going to try to hand that stuff back on Monday. Okay. So the question will be, if you're not healthy, you probably shouldn't take it today. But maybe be prepared to take it on Monday. And since I'm handing it back probably Monday during class, is that okay?
Yeah, that will work. I told some joke about Pi Day. I forgot. Is that today?
Tomorrow.
Tomorrow?
Today's Friday the 13th. Tomorrow is 3/14.
Oh.
Pi Day. So yes, you should celebrate.